Hi everyone, my name is Jenna Douglas, and today we are going to be discussing Graham's law and the purification of gases. By the end of this lecture, you should know the difference between effusion and diffusion, what similarities do they share and how are they different, and also what is Graham's law of effusion and describe what it is used for. How does Graham's law of effusion relate to the kinetic molecular theory? And finally, you should be able to describe the real-life applications of Graham's law. So we know the rate of gas molecules move depends on their average speeds. Their average speeds can get impacted by the temperature and pressure and the molar mass of the gas. The two processes that affect the movement of gas molecules are called diffusion and effusion. Diffusion happens when the lower concentration zone is filled with other gases. This causes the molecules to mix and collide with one another. And this happens when a barrier is absent. Effusion, on the other hand, happens when the lower concentration zone is empty and there is an escape of gas molecules from their container through a very small hole in a vacuum. This hole is also known as a pinhole, and these gases move without collisions. This is a textbook definition of diffusion. As you can see, hydrogen molecules initially diffuse farther through the nitrogen molecules because hydrogen is lighter, although once you remove the barrier, the molecules will intermingle in the closed container. On the contrary, this is a textbook definition of effusion, and this is a diagram to go with it. So effusion occurs when there's a tiny pinhole present in the container, and this pinhole will turn into a vacuum, and the molecules will be able to escape from their container. In this figure, you will now see the lighter hydrogen molecules effuse faster than the heavier nitrogen molecules. This is an animation of the rate of effusion of a gas. After watching this animation, take notes of what you noticed is different between the two gases with a pinhole and without a pinhole present. This is very good practice if you want to see a real-life diagram of what effusion and diffusion will look like in live action. Now that we saw that animation, we came to the conclusion lighter, faster gas molecules find the pinholes more frequently than heavier, slower gas molecules. Therefore, we can make the conclusion the molar mass must play a significant role in the rate of effusion. Now that brings us to Graham's law of effusion. Thomas Graham is a British chemist who created the law known as Graham's law of effusion. His law was initially trying to explain the motion of molecules in general, but he was only able to calculate the rate of effusion. And we will figure that out on why he was only able to do that later in this lecture. But for now, the equation describes that the rate of effusion of a gas is inversely proportional to the square root of its molar mass. We can develop an expression for comparing the relative rates of effusion of two different gases. Let's just use gas 1 and gas 2 for this example. So gas 1's rate of effusion is equal to 1 over the square root of its molar mass, and same with gas 2. Gas 2's rate of effusion is equal to 1 over the square root of its molar mass. Keep in mind, this is only if they have the exact same temperature and pressure. The overall equation is the rate of effusion of gas A over the rate of effusion of gas B equals the molar mass square root of mass B divided by mass A. This equation can be used in a variety of ways. For example, determining which gas diffuses faster. An effective way to find this is to note in every case a ratio of effusion rates, distance, times, etc. is equal to the square root of a ratio of molar masses. There are many limitations to Graham's law that we need to take into account. So Some are Graham's law is available for diffusion only for gases that occupy low pressures. This is because molecules have to have the chance to individually escape through a pinhole and not as a clump of molecules. As well, the pinhole must be very, very tiny, so collisions aren't occurring as gas molecules pass through. When talking about diffusion of a gas, this law only applies to a fusion. This happens because the molecules of a diffusing gas undergo collisions with other gas molecules, unlike a fusion. Although diffusion does occur, but we cannot use Graham's law to make quantitative predictions about the rates at which the gas molecules diffuse. So in other words, we simply just can't use this equation for diffusion because it's simply not accurate enough. We will not get an approximate answer simply just because there are collisions occurring between the molecules, which in the end will impact the rates at which diffusion occurs. So this is an example of relating times of fusion to molar masses. A sample of argon gas escapes through a tiny hole in 68.9 seconds. The exact same amount of an unknown gas escapes through the hole in 55.8 seconds, under the same conditions. What is the molar mass of the unknown gas? So I suggest you do this problem first, and on the next slide you can see if you got the right answer or not. So first, before solving any problem, make sure you write what is known in order for you to have all the variables to solve this problem. So we need to use the equation rate of diffusion for unknown gas over the rate of diffusion for the known gas, which is argon in this case, is equal to the square root of the molar mass of the unknown over the square root of the molar mass for the argon. So we know the molar mass of argon because if we look on the periodic table, we can see that it's 39.95 grams per mole. We can also fill in the values for the rate of diffusion for both values being 55.8 and 68.9, and you can divide them by each other to get a simplified value. Now, in order to solve for the molar mass, we have to square root each side. Now we have to cross multiply 0.810 seconds squared by 39.95 grams per mole, which is the molar mass of argon. And finally, after calculating this, we will find that the molar mass of the unknown is 26.21 grams per mole. The derivation of Graham's law first begins at the recognition that the rates of diffusion is directly proportional to the area of the pinhole and the rates at which the gas molecules collide with the pinhole. The rate at which gas molecules collide with the pinhole is directly proportional to the average speed of the molecules and the number of molecules per unit volume, or the number of moles per unit volume. In other words, we can conclude the faster the molecules move, the greater concentration and the greater rate of diffusion. The kinetic molecular theory states that the average speed is equal to the square root of 8 times R times temperature over pi times molar mass. Now, if we plug this into our equation above, we can get the rate of diffusion equals the constant times the area times root 8 RT over pi times molar mass times pressure over RT. Graham's law can be used in the separation process of gases with different densities by comparing the rates of diffusion and the molar masses of the unknown substance in the known gas. So you're probably wondering now, why is this useful to me? And has this ever been useful in the past? Because that's what I was wondering when I was first researching this topic. So actually there's an answer to that. So scientists can separate the isotopes of a given gas. An example of this is Graham's law was used in World War II to build the first atomic bomb. This is also known as the Manhattan Project. Scientists wanted to separate uranium 225 from uranium 238, which was found in natural uranium ore. After they built a different diffusion plant, uranium from uranium ore was converted into uranium hexafluoride. After this, the uranium hexafluoride was repeatedly diffused, becoming more enriched, and became a slightly lighter uranium 235 isotope. This is important because this has something to do with the purification of gases, which is the main topic of this lecture. The enrichment process requires uranium to be in gaseous form at relatively low temperature. Hence, uranium oxide from the mine was converted to uranium hexafluoride. And hence, this uranium hexafluoride was repeatedly diffused and becoming more enriched and actually became slightly lighter, which is a result of this diffusion process. I hope you understood the core concepts discussed today in my lecture I created, and here's a summary of what we've discussed today. So we discussed simple gas properties, Graham's law of diffusion, we did some sample problems, we learned about the limitations of Graham's law, the derivation of Graham's law, and the applications of Graham's law that was used in the past and is still being used in the present day.